So in the previous lesson, you did an exploration where you were looking at the derivatives of power functions. You looked at x, you looked at x squared, you looked at x cubed. And I actually think we put some a values in front of these. And I think for a lot of you, you might have been able to summarize that you expected the derivative of this to look like a times n times x to the n minus 1. So that seemed to be the conjectures that a lot of you came up with when you finished that exploration. I think we went out to the 5th, and then I asked you to predict what you think it would be in general, and a lot of you sort of came up with that formula. So that's not a proof. So what I'm going to attempt to do today is we're going to attempt to try and prove it. So for this particular case, we did see that it looked like that f prime at x was 0. So what would a formal proof look like? And so for all of these, I'm just going to explain what we're going to be doing. We're going to have to be doing the limit as h goes to 0 of f at x plus h minus f at x, all divided by h. And then we're going to walk through different functions. And once we've proven it, then you can use it. So you thought it looked like the derivative for this particular guy was 0, and maybe you justified why that's true. If we're a constant, we're a horizontal line, and the slope of all horizontal lines would be 0. So that does indeed make sense. So what's that going to look like if we prove it from first principles? Again, we're going to use that limit definition. F at x plus h, well, it's a constant function, so it's always going to be a. This is a constant function, it's going to be a. So a minus a is 0, 0 divided by any number is 0. We have the limit as h goes to 0 of 0. I now got 0 back. So now we've proven it. We've proven that if f at x is a, then f prime at x is 0. Yesterday, when you did this, or not yesterday, or the previous lesson, because I'm not sure how many lessons we're going to be doing a day, f at x is ax, then f prime at x was a. And if we think about logically why that would make sense, you've got a line. The slope of this line, here's the line is ax, the slope of that line is a. And since f prime at x is the slope of the tangent anywhere, we're expecting that to come back as a. And how are you going to prove that? Again, you're going to plug into this definition. That's the definition of derivative, and you're going to do the math and work it out. Again, you can be in control of timing. I'm just going to move to the next slide and show you what that would look like. So f at x plus h, we're now going to plug in x plus h where that is. So we have a times x plus h minus ax. If we expand, we get ax plus ah minus ax. Note, those go just like it has all along. Any term that doesn't have an h drops out. I now have ah over h. And of course, h divided by h goes, and we're just left with a. The limit as h goes to 0 of a is going to be a. So we've now proven that if the function is ax, that f prime at x would be a. And now let's move on to the next example. In the next example, what if it is ax squared? You looked at this one in the previous lesson. We found that f prime would be 2 times a times x. How are you going to prove it? Again, we're going to come back all the way to this. You're going to use this definition, but you're now going to be plugging into the function ax squared. Again, you can be in control of the timing. I'm just going to move you forward to show you what that would look like. There we are, first principle definition of derivative. I'm now going to plug in x plus h right in here. So I'll get a times x plus h all squared minus f at x is ax squared. Now going to expand this. This is going to be x squared. X times h times 2 is plus 2hx. H squared, h times h is h squared, so we get to here. Distribute the a, we get ax squared plus 2ahx plus 8h squared minus ax squared, which was f at x. Notice those two go. Any term that doesn't have an h will have an additive inverse. That brings me down to here, 2ahx plus 8h squared, all divided by h. But now each term here can be divided by h. So if I divide the first term 2ahx by h, I will get 2ax. If I divide ah squared by h, I will get ah. And now when I send h to 0, this will become a times 0. Of course, that's just going to be 0. So I'm just going to be left with 2ax. So we've now proven that if f at x is ax squared, then f prime at x is 2ax. All right, this is the last one you're going to attempt to be doing on your own. So yesterday, when you looked at this one, we found that f prime at x was 3ax squared. So you're going to prove that again, all the way back to our first principle definition. And you can be in control of the timing once again. It's probably best that you do try this on your own and see if you can show that this is true. I'm just going to move forward to the next slide and show you why it's true. So first principle definition, back to here again. I'm now going to be plugging into this equation. So x plus h into here, I now have a times x plus h all cubed, minus ax cubed, all divided by h. I viewed it this way, so it made the expansion easier. So I'm going to expand the squared first and get x squared plus 2hx plus h squared, all times x plus h. And I'm going to multiply by the a at the end. Expanding, that times that is x cubed, that times that is plus hx squared, that times that plus 2hx squared, that times that is plus 2h squared x, that times that is plus h squared x, and that times that is plus h cubed. Now I need to distribute the a across all of these. And I'm just going to pause momentarily. All right, so first off, I'm just going to collect like terms. So we've got h x squared, and we have 2hx squared. That's 3hx squared, 2h squared x plus h squared, and there we go. Now I don't know what you remember about Pascal's triangle. So 1, 2, 1. Then we get 1, 3, 3, 1. This is the squaring row. This is the cubing row. So your coefficients for these are supposed to be 1, 3, 3, 1, and that's what we're getting. 1, 3, 3, 1. And now when we multiply by a, notice this ax cubed here is going to drop out that ax cubed. I'm going to get 3ah squared plus 3ah squared x plus ah cubed. Each of these terms now is divisible by h, so dividing this term by h, the h's will go. I have 3ax squared. 1h will go here, and I'll be left with 3ahx. I'll lose an h there, and I'll be left with plus ah squared. Sending h to 0, these terms will become 0, and I will be just left with 3ax squared. We've now proven that f prime at x is 3a x squared. Oh, 3a x squared. Clean that up a bit. All right, now in this particular one, I'm just going to walk you through what it would look like for a x to the fourth. I know what to expect. I'm expecting that f prime would be 4a x cubed. So plugging into the function here, I'm now going to have a times x plus h to the power 4 minus a times x to the fourth. I'm going to split this up into two squared pieces. X plus h all squared is going to expand to that. The other x plus h all squared will expand to that. And when we multiply these two together, I'm going to get 9 terms in this particular expansion. To make life easier for myself, I factored the a out. I should probably mention that on this step, so I didn't have to worry about that to the end. I factored the a out, and I've written it out in front. Now, expanding, there's the 1, 2, 3 terms that would represent this guy by this bracket. The next 3 terms, 1, 2, 3, represent multiplying this guy by all of the terms in this bracket. And the last 3 terms from here to here represent multiplying this guy by that bracket. If you need time, you can pause the video just to verify that these are correct. I also color-coded them so that they would be in the correct color so we can see the pieces that belong together, that are going together. So we see the x to the fourth drop off. These two come together to give me 4hx cubed. All of those come together to give me 6hx squared. The greens come together to give me 4h cubed x. And then I just have the h to the 4th sitting on the end. And if you want to use Pascal's triangle, again, we could still do that. So that's 1, 2, 1, 1, 3, 3, 1. We're now on the row for the power 4. We should be getting 1, 4, 6, 4, 1. The original one was this x to the 4th. There's the 4, 6, 4, and then that one. Now notice all of these terms that are left just involve h, and we can now divide. So this divided by this is giving me 4x cubed. Now expanding, multiplying by the a as well. 4a x cubed, get rid of an h there, times by a. We get 6ah x squared, get rid of an h here, multiply by a, 4ah squared x, and here, get rid of an h, multiply by a, I get ah cubed. Now, if you send h to 0, since all of these pieces involve an h, products of h's, they're all going to be 0, and we're just going to be left with 4ax cubed. So we've now proven that if f of x is a times x to the power 4, that f prime would be 4 times a times x cubed. Now, we've proven it for 5 cases, I believe. We haven't proven it in general. I would then have to go out to, x to the 5th, x to the 6th, and clearly we cannot do all of these one at a time, right? I hope that makes sense to you. There's an infinite number of possibilities for this exponent. The proof in mathematics cannot be a proof by exhaustion, which means prove it for every single number that we could possibly put in here, because that would never end. So I'm going to walk you through a couple of proofs of this. The general proof of this you are going to do yourself when we get to, I believe, Unit 4, to prove that it works for all real numbers. I'm just going to walk through this one here. And I'm going to use the binomial theorem to expand this. And in this particular case, then I'm going to be assuming that n is a natural number. I can only use the binomial theorem if n is a natural number. So x plus y to the power n would be n choose 0, x to the n times y to the 0. N choose 1, the x's drop, so we go x to the n minus 1. They go down by an exponent, and the y's come up. N choose 2, the x exponent has dropped by 1, the y exponent has gone up by 1. That would continue, and on the back end, when we're finished, we would have exponent x to the 0, y would be up to the power n. Coming over here, notice this one is 1 more, coming this way 1 less, coming this way 1 more, coming this way 1 less. This is n choose n minus 1, this is n choose n. So this is how you would expand this, and now we're going to use this. In the general case now, I do know what the derivative is supposed to be. F prime at x is supposed to be n times a times x to the n minus 1. Or we can write that as a n x to the n minus 1. Now we're going to try and prove that. So we're going to plug in. We're going to get a times x plus h to the power n minus a times x to the power n. Just like in the previous question, I'm going to factor that a out, and I'm going to get x plus h to the power n minus x to the n. Now I'm going to use the binomial theorem to expand, and I know this is an infinite list, and I'm going to plunk that infinite list in here. N choose 0, x to the n, h to the 0. N choose 1, x to the n minus 1, h to the 1. N choose 2, x to the n minus 2, h squared, plus dot 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 dot. N choose n minus 1, x to the 1, h to the n minus 1. N choose n, x to the 0, h to the n. And then there's the minus x to the n from there. Now, if you have n items and you choose none of them, there would be only one way to do that. So this would be equal to 1. And of course, this is equal to 1. So I'm just going to be left with an x to the n. If you have n items and you want to choose one of them, there are n ways to do this. So this is n. So I get n times x to the n minus 1 times h. Now the rest of these I'm not going to worry about what this evaluates to, any of these other pieces, because when we do our division, we have one extra h here, So that's going to drop out. I have an extra h in the next one. And all the way along, all even up to including this one out here, those will all have extra h's. So it doesn't matter what these numeric coefficients evaluate to, because they're going to drop out when I allow h to be 0. So the only ones I were worried about were these first two where I know I didn't have an extra h. Now this x to the n will cancel out that x to the n. On the end here, if you have n items and you choose n of them, there's only one way to do that. And x to the 0 is 1, so this last term was just going to become h to the n. But again, it wouldn't be necessary to simplify that one out. So after the x to the n's drop off, I have n times x to the n minus 1 times h plus n choose 2 times this bits. And there's a whole bunch of bits in here, but notice they all have extra h's. When I now divide by h, this piece doesn't have an h, this piece keeps an h. The next one will be h squared, h cubed, and so on, all the way out to the last term, which will end in a times h to the n minus 1. But because these all involve an h, when we plug in our 0, these will all be 0. And what I will be left with is this piece here. And now my derivative is a times n times x to the n minus 1. So I'm able to prove this using the binomial theorem, but I've only proven it for all natural numbers, because you can't use the binomial theorem if your exponent is not a natural number. So here's a bit of a summary. What's the power rule? So the power rule states that if we have the function x to the n, where n, I did prove this for natural numbers only, but it works for all real numbers. So if n is a real number, then f prime would be n times x to the n minus 1. If you have a constant times x to the n, where n is any real number, then its derivative g prime would be a times n times x to the n minus 1. So these are the power rules. This is the only derivative rule that we're going to use in this particular unit in terms of finding an actual derivative. And then I will show you how to take derivatives in later lessons of products, sums, quotients, etc. All right, now I'm going to show you a different proof. I showed that it was true. I put W, but I'm going to say N because you should be okay with me saying that the natural numbers are 0, 1, and 2, and so on. That's the definition they use in university. In high school, we might have split this into two number sets. Natural being 1, 2, and 3. W, whole numbers, will add 0 to the set of whole numbers. In university, they use N, and if they want just the positive whole numbers, they'll call this bit N plus. So I'm going to call that N. All right, so now I'm going to try to show you that it works. We can do a proof for rational exponents. So I'm going to start with f at x is x to the p over q, where p and q are natural numbers. I want to show then that f prime at x would be exponent comes out in front, x to the p over q minus 1. So the first thing I'm going to do is I would like to raise both sides to the power q. So if I raise both sides to the power q, whoops, let's get the pen back. If I raise both sides to the power q, I get y to the q equals x to the p over q times q. P over q times q is just going to be p. So I'm now here. Y to the q equals x to the p. And what I'm going to do at this point in time is I'm going to take the derivative of both sides with respect to x. Now, this little bit, I know you don't understand implicit differentiation. We'll learn more about that later. You're not going to be tested on that in this unit. In fact, when I present this to you, it would only be in the context of a performance task. So to find the derivative with respect to x of this, we need to do it this way. We need to do d by dy of y cubed times dy, not y cubed, y to the power q. So if I want to take the derivative with respect to x of y to the q, I have a mismatch on variables. So we do what's called implicit differentiation. Take the derivative of this with respect to itself, and then multiply by dy by dx. And then you can see, because you imagine these sort of as partial derivatives, that you see how that those could reduce out and I'd be back to where I started from. So that's how I can convince you that this is going to return d by dx. And now this bit we can do. Whoops. This little bit we can do. How do you take the derivative of y cubed with respect to y? Well, the q comes out in front, and we have y to the q minus 1, and now we need to multiply by dy by dx. I can take the derivative of this with respect to x by bringing the exponent out in front, x to the p minus 1. Now what we are trying to do is we're trying to find dy by dx. dy by dx is y prime, or f prime at x. They're all synonymous, so what I'm going to do is isolate for this by dividing by this. So dy by dx is p to the x to the p minus 1, all divided by q times y to the q minus 1. Now what am I going to do at this next step? What is y? We know that y is x to the p over q. So I'm now going to replace this with x to the p over q right here. So q, replace the y with x to the p over q, all to the q minus 1. Now dy by dx would be equal to q times a power of a power. I'm going to multiply those. So p over q times p over q minus 1. So that becomes p over q times q minus p over q. This just becomes p. So I now have dy over dx is p times x to the p minus 1 all over q times x to the p minus q. I now have p over q, and if you divide two powers with the same base here, you're supposed to subtract the exponents. So it's p minus 1 minus p over q. Distributing, that's p minus 1 minus p plus p over q. The p's will go, and I'm now left with p over q minus 1. So I was now able to prove that this will work for positive rational exponents. So if we had x to the 3 halves, positive rational exponents, the derivative of that would be 3 halves, x to the 3 halves minus 1. So I now proved that for positive rational. The technique I need to do to prove it in general, we don't know anything about that yet, so we'll save that for the general proof. This will be the one time in a course where I will say, look, it works for everything. I can't prove it to you at this point in time, but trust me, it does work. We will prove it later. This power rule works for all real numbers. We've just proven it up to and including positive rational numbers. All right, now we're going to practice taking derivatives. Now remember, they need to be in this form, which I'm going to call power rule form. We'll check. This is in the correct form, so we're ready to take its derivative. All right, so I just was attempting to recover from that spinning wheel. This is in the correct form, so we can take the derivative. I'll show you that on this particular slide. We call that massaging. It's not necessary to massage this, as it already is a power function. So its derivative would be negative 4. The exponent comes out in front, times 3 times x to the 3 minus 1. That gives me negative 12 times x squared. All right, we'll move on to the second one. Again, I want you to look at that. Do we need to massage first? No, this is a power function. The exponent now is an integer. It's a negative integer, but remember the power rule still applies. So we can bring that exponent out in front, times x to the, and then we can take 1 away from the exponent. That's going to look like this. Y prime is negative 3 halves times negative 2 times x to the negative 2 minus 1. This is positive 6 over 2, which is 3. Negative 2 minus 1 is negative 3. So if this is y, its derivative is 3x to the negative 3. Moving forward, we'll take a look at this one. Now notice what I did. I started with a nice natural number exponent. I've moved to an integer exponent. Same rules apply, they still work. And now I'm moving to a positive rational exponent. Again, this is still a power function though, so we can still take its derivative. Multiply my constant a by the exponent and then take 1 away from the exponent. Still applies here. Again, as I mentioned, not necessary to massage, it is a power function. So it will be 3/8 times 2/3 times x to the 2/3 minus 1. this becomes 6 over 24, which reduces to a quarter. And that will be a bit more challenging when the exponents are not whole number values, either integers or natural numbers, because we're going to have to think of a common denominator. This is 2/3 minus 3/3. That's negative 1 over 3. So the derivative is 1/4 x to the negative 1/3. All right, now we're going to move on to this next one. This one, I hope you can see when you're looking at it, this is not a power function. It does not look like this. It does not look like a times x to the n. What it looks like instead is a times x all to the n. And so there's an exponent law that helps us handle this. This is a to the n times x to the n. So this is an example where we're going to need to massage first before I can take the derivative. Because again, this derivative can only be applied, this derivative rule, if the function looks like this. So this is not a power function, as I mentioned. Massage first. So 3/2 to the 32, it's not 3/2, 32 to the negative 3/5, x to the negative 2, all to the negative 3/5. And notice how I've written y here. I have not written y prime. I am not taking a derivative at this point in time. I'm simply massaging the function first. So I need to make that clear to the person who's grading my work by putting a y out in front of this. All right, let's do this way. The 5th root, so this is 32. I'm just going to handle it this way. We're going to do to the 5th first, and then to the negative 3 after that. So the 5th root of 32, I can't even write a 5 with this, 5th. The 5th root of 32, that's what I'm doing. The 5th root of 32 is 2. So then this is 2, becomes 2 to the negative 3. 2 to the negative 3 is 1 over 2 cubed. That becomes 1/8. So simplifying that part, we have 1/8. X to the negative 2 to the negative 3/5, power of a power, I'm going to do negative 2 times negative 3/5. And that is going to become positive 6 over 5, so 6/5. So after I massage this, I'm going to get y is 1/8 x to the 6/5. I'm now going to note that x can't be 0. How do I know that? Because this was initially in the denominator, so we could not let x be 0. And if I write it this way, I'd lose sight of that fact, because the derivative is not going to exist when x is 0. All right, it is now a power function. Now we are ready to take the derivative. Again, that comes out in front, and we take 1 away from the exponent. So we have 1/8 times 6/5 times x to the 6 over 5 minus 1. That's 6 over 5 minus 5. See if I can get better at writing these 5s. Minus 5 over 5. That's 1 over 5. 6 over 40 reduces to 3 over 20. So the derivative is 3 over 20 times x to the 1/5. And again, I'm just going to remind you, put a y in front of it when you're massaging. You might even want to make a note. Santa, I'm massaging and simplifying first. Now I'm taking the derivative. And note I had a y prime down there. All right, let's look at the next example. This example here wants us to find the equation of the tangent to y equals negative 4 divided by the 4th root of x all to the power 3 at the point 1, negative 4. So to find the equation of the tangent, I'm going to need the slope. In order to find the slope, I need to do f prime. But I can only do f prime if it looks like a times x to the n. So the first thing I'm going to ask you is this in the correct form? Is this in power function form? It turns out it's not, so the first thing I need you to do is write that in power function form. So again, not a power function, so I'm going to massage it first. I'm just going to show you that, maybe I'll just work this part of it. How did I get these numbers? All cubed. This is 1 over x to the 1/4. That's what the 4th root means. It's x to the 1/4 all cubed. We do a power of a power here. We're going to multiply those two exponents. So 1/4 times 3 is 3/4. And then I have to move it. We can't leave it. That is a power function, but it's not 1 over a power function to find its derivative. It needs to look like this. It's not 1 over that. So then I'm going to have to move this up to the numerator, and when I switch it, its exponent is going to become negative. So as a power function, this would be y equals negative 4, x to the negative 3/4. And again, I am going to note that x can't be 0. Couldn't be 0 here. we would lose sight of, well, we probably wouldn't lose sight of that fact over here because we can see that the exponent's negative there. All right, now that we have it in the proper form, you're now going to take the derivative of it. And then after you take the derivative, then we try and find the slope. So the next step, take the derivative. Again, you can be in control of the timing. I'm just going to move this one forward. We take the derivative now. We get -4 times -3/4. And then the new exponent becomes -3/4 minus 1. That's -3/4 minus 4/4. That becomes minus 7/4. This is positive 12/4, and that becomes positive 3. So there's the derivative of that. So if y is -4x to the -3/4, its derivative is 3 times x to the -7/4. Again, to find the derivative of a x to the n, it is a times n times x to the n minus 1. So multiply the constant by the old exponent, the new exponent, take 1 away from the old exponent. All right, now to find the equation of the tangent, we need the slope. So the next step would be find the slope of the tangent when x is 1. Again, you can be in control of the timing. I'm just going to move this forward. So now what we're going to do, a proper notation to show someone what you're doing, is we want to find y prime at 1. To find the equation, slope of the tangent when x is 1, you can say that in math by writing this. Y prime at 1 is 3 times 1 to the -7/4. 1 to any exponent is 1. 3 times 1 is 3. So now we know what the slope of the tangent is. And remember, the equation that we're using is point slope form, m times x minus x naught. So we have everything we need now to finish off. We have x naught, we have y naught, and we have our slope of our tangent over here. And so let's just finish that off on the next slide. As I mentioned before, the fastest way is to use the point slope form. So I'm going to do y minus y naught. Y naught's -4, so y minus -4 equals, the slope of the tangent was 3, times x minus x naught. The x coordinate of that point on the tangent line, or the point of tangency, is 1. I plug in a 1 there. I now get y plus 4 is 3 times x minus 1. And as we mentioned before, we're going to leave it in that form. If you prefer, I'm not saying you have to, if you prefer, you could isolate, because now we're going to get 3x minus 3, bring the positive 4 over, it becomes minus 4, 3x minus 7. But again, as I've mentioned before, in university, or profs are happy if you leave it in this form, so I'm happy if you leave it in that form. If you try to go from this form to this form and make a mistake, marks could be deducted. All right, next question. Where will the tangents to this curve have a slope of 4? So this is what we're trying to find. We're going to change that from English to math. Where is f prime at x equal to 4? Anytime we're talking about slopes of tangents, we're talking about f prime. So now we need to know where f prime is 4. So of course the first step is find f prime. First question I'm going to ask you, is that in the form it needs to be? Is that a times x to the n? If it isn't, then you're going to have to write it in the correct form. Again, you can be in control of the timing. I'm just going to move forward. It is not a power function, so I'm going to massage first. 1 over x to the negative n, exponent laws, that's x to the n. So massage first using this exponent law. I'm now going to rewrite this as 3x cubed, x not 0. This time I do have to write it, because if you saw the function written this way, you would not know that x couldn't be 0. X can't be 0 based on how this one is written. So now we want to know where that would have a slope of 4. Well, actually, we're not even that far yet, because we've just found f at x. We now need to find f prime. It is now in the correct form. It looks like 8 times x to the n. Again, you can be in control of the timing. I'm just going to move forward at this point. We're now going to be, how did the teacher get that? It's 3 times x to the 3 minus 1. As we move forward, I'm going to stop doing all the extra writing. 3 times 3 is 9, 3 minus 1 is 2. So f prime is 9x squared. I now want to find where f prime at x is equal to 4. So then we're going to solve that particular equation. You can set that up and solve it. Again, you can be in control of the timing. I'm just going to move forward. Now I need to solve 4 equals 9x squared. And jumping forward, that's going to give us 4/9 is x squared. I now need to take the square root of 4/9, but I'm going to remember there are two possible places that could occur. Plus or minus when you take the square root, right? Because you can square a negative and get a positive. So it's plus or minus the square root of 4/9. And that gives me plus or minus 2/3. Now think about this logically. So I'm going to make this a little bit thinner. And let me say that a slope of 2/3, that's approximately a slope of 2/3. So I'm going to bring that up, and notice how we're going to intersect that once to the left of the axis, and then we would intersect again somewhere over here to the right. So there's two places where we would hit that slope. That's reasonable. So I expect there to be two places, and we found two places. Let's jump back over here. Let me just think about this for a sec. All right, so what I was considering now was, it says where. And where is kind of ambiguous, right? Does where just mean the x coordinate, or does it mean both? So let's suppose it means both coordinates. Then we would be looking at 3 times 2/3 to the power 3. And that's going to give me 3 times 8 over what, 27? And that is 8 over 9. And then when we plug in negative 2/3, we'll get negative 8 over 9. So we're 2/3, 8/9. And then we're negative 2/3, negative 8/9. But again, a little bit ambiguous. I'm not sure that I should include the y coordinate. Where is not a very descriptive term. So again, nice example to put these down, because this is university, you have to tell them what your assumptions are. My assumption was that when you said where, you meant only the x coordinate. Or my assumption is when you said where, I assumed you meant both the x and y coordinates, so I'm giving you both. And then you can be prepared to argue for marks in university. And the last question we're going to answer now is it possible for the slope of the tangent to be negative 3? And then you have to explain. Again, I'm just going to move forward, finish this off. F prime at x is 9x squared. That's a parabola, right? And the slope of a parabola is never going to be able to be, or not the slope, the slope is this parabola. And is that ever going to be negative? No, it's never going to be negative. There is no solution to negative 3 equals 9x squared, which is what I'm trying to tell you. This is greater than or equal to 0. The smallest it can be is 0, because that was a parabola. This is less than 0. So there's no way these two can be equal to each other. Alternately, another way to look at this is we did say that we could rewrite this as 3x cubed. But x not 0, it's not really the true shape of the graph, because I do know that I should have a vertical asymptote here. But the curve is always increasing. And if the curve is always increasing, then the slopes of the tangent can never be negative. So it would be impossible for that to happen. All right, so that brings us to the end now of lesson 3. What was the big idea for lesson 3? Back us back up to there, is we now know how to take the derivative of a power function. And we practice rewriting. If it doesn't look like this, then I'm going to have to rewrite it in this form before I can apply this rule. And then what we will do is we're going to extend upon this. What happens when we have sums, differences, products, and quotients. That'll be what this balance of this unit is about. So that brings us to the end of lesson 3. If you made it to the end, thank you for your support. Hopefully you've learned something. Stay tuned for the next lesson. And as always, take care.